All right, in Chapter 9, we're going to talk about tests of significance for non-parametric measures. Okay, so t-tests and f-ratios require normally distributed data that's at the interval level, okay? So those are referred to as parametric tests. What do we do if we can't meet those requirements? Well, we're going to use non-parametric measures. And the one that's probably most important for us is the chi-squared. It looks like it says chi-squared or chi-squared, but that's pronounced chi. Okay? There's a median test, a Mann-Whitney U test, and a Kruskal-Wallis test. So these are less powerful than parametric tests. So, when we talk about these, when we're talking about power, we mean the probability of rejecting the null hypothesis when it is actually false and should be rejected. So much of the data in criminal justice, as we've seen when we're dealing with the GSS and with some of our NIBRS variables, is that it's not interval level data. Okay, we also know that some of our data is skewed, right? Or it might not be large enough. Okay, so we're going to first talk about chi-square, one-way and two-way chi-square tests. So imagine the correct answers to a test are distributed as follows. You want to know if the teacher has a preference for a particular letter as a response. So sometimes people think like, oh, guess C if you don't know the answer because teachers pick C as the response a lot. So our null hypothesis is the instructor has no tendency to assign any particular correct response from A to E. The research hypothesis is that the instructor does have a tendency to assign a particular correct response. Well, we can't just look at the data and say, yep, this teacher prefers B. So what are the expected frequencies, right? If the null hypothesis is true, right, there's no difference. They should be equally distributed. 10 A's, 10 B's, 10 C's, 10 D's, and 10 E's. Imagining E as a grade. That's kind of weird. So a chi-squared lets us test the difference between what we actually observe, which is on this prior page, versus what's expected, which is on this page. Okay, so the observed frequencies are the things that we actually observe happening, and the expected frequency is what should happen under the null hypothesis. So chi-squared allows us to test the significance of those differences. Okay, and so chi-squared, that's at italics looking X, is equal to the sum of the observed frequency minus the expected frequency squared over the expected frequency. So let's do this. We're going to set it up as a table, right? So FO is our observed frequencies and FE are our expected frequencies. We're going to subtract them and square them, okay? Then we're going to divide that by the expected frequency. Or divide that by the expected frequency. And in this case, we get a chi-square of 4.6. Okay? Now, the other thing we need to know is the appropriate degrees of freedom. So here it's k minus 1. Here, k, instead of n, is the number of categories. So we have 5 categories minus 1 is 4. Okay? We're going to go into our table F, which has chi-square values. Okay? And we're going to see the critical value for 4 degrees of freedom is 9.488. We have to exceed that, okay? So our calculated chi-square is only 4.6, okay? So this teacher does not have an underlying preference. Okay, let's look at another example. Juvenile offenders are equally divided in their perceptions of how aggressive police officers are, and our research hypothesis says they are not, okay? So we survey 60 juveniles and 35 believe the police have become more aggressive, 10 think they are less aggressive, and 15 think they are about the same. Okay, so we've got our categories, more, less, and the same, and then we have observed and expected frequencies, right? So our expected frequency should be 20, 20, and 20. Okay? We're going to just move to the next step where we're going to set up that table. Okay? So we're going to subtract the expected from the observed, square it, and then divide it by the expected. Okay, so in this case, our chi-square is 17.5. Degrees of freedom here is 2 because we have 3 categories. So let's go back to our table, okay? And the critical value here is 5.99. Well, we more than exceed that, right? Because our chi-square is 17.5. So yes, these findings cannot be passed off as just chance. What happens though if expected frequencies are not equally distributed? Okay, so maybe we have some external benchmark we're using. So imagine a criminologist wants to study racial profiling and traffic stops by police. So she's going to compare the race ethnicity distribution of drivers, white, black, Latino, with a random sample of 250 traffic stops. Now they're comparing them instead of saying like we should have equal amounts of white, black, and Latino drivers. They're going to compare them to the state's population of licensed drivers. Okay, so that's 70% white, 20% black, and 10% Latino. Okay, so we have our hypotheses and we have our data right here. Okay, so we're going to break them down into percentages. Okay, and then what we're going to do is we're going to have our excuse me. Yep, okay. Then we're going to have our table here, our observed frequencies plus what we should expect. Okay, so out of 250 drivers, if 70% are white, 175 of them should be white. We're going to literally set up the exact same table and do all the same things. So chi-square here is 8.4, right? And the critical value of chi-square that we need is 5.99. So yes, the race ethnicity distribution of drivers in traffic stops does not match that of licensed drivers. How can we compare observed and expected frequencies for more than one variable? Well, here we're going to use crosstabs, okay, and we're going to do a two-way chi-square test. So crosstabs are used to compare the distribution of one variable across some other category, right? So maybe we're going to look at, do you use your seatbelt? Yes, no, and we're going to break that down by men and women. So these are very similar. In fact, we're going to use the same formula, and the only major difference is in how we calculate expected frequencies. So expected frequencies are going to be the row marginal total times the column marginal total divided by n. So here's an example, right? We're going to look at the percentage of liberals who are lenient is not the same as the percentage of conservatives who are lenient, right? So here we've got our actual observed frequencies on the left. 13 liberals are lenient, 7 conservatives are lenient, 7 liberals are punitive, and 13 conservatives are punitive, right? So that gives us a total of 40, an N of 40, okay? If this were evenly distributed, it should be 10, 10, 10, 10. Okay? So we're going to have our observed frequency in table 9.2, and then we have our expected frequency. We put it in parentheses. Okay, so we have our column marginal total and our row marginal total. And then we're going to create a very similar table that we just did. Okay, so we learned that our chi-square is 2.66. But in order to get our degrees of freedom here, we're going to take the row minus 1 times the column minus 1. Number of rows times number of columns, each minus 1. Our degrees of freedom here are 1. So we have a chi-square of 2.66 with a degree of freedom of 1. Our calculated chi-square is only 2.66 and therefore smaller than the table value, so we have to retain our null hypothesis. Okay, so when we're finding expected frequencies for each cell, they have to reflect the operation of chance under the terms of null hypothesis. So they have to be proportional to their marginal totals for rows and columns. And we've got an example here to the right. One of the few demands on the chi-square test, though, is that the sample size should not be too small. So we want to be wary of any expected frequencies that are less than 5. So if that's the case, we need to collapse our categories. We might collapse, race into white, non-white, as opposed to white, black, Asian, etc. So when the expected frequencies are greater than 5 but less than 10, we also want to use what's called Yates correction. Okay? We only use this for 2x2 tables. So that means chi-square is going to be the sum of the absolute value of observed frequency minus expected frequency minus 0.5 squared. So here we've got our same thing we're going to look at. Okay, now we're going to look at, does hypnosis affect the recognition memory of eyewitnesses to a crime? Okay, so all subjects first view a videotape of a pickpocket plying his trade. 1 week later, they're randomly assigned to one of two conditions. The subjects in the experimental group are hypnotized and then asked to pick the thief out of a lineup. And the subjects in the control group are not hypnotized and try to do the same identification. Okay? Only 7 of the 40 subjects in the experimental group were correct, whereas 17 of the 40 control subjects made the right choice. So this may suggest that hypnosis does have an effect, although a negative one. But is that a significant difference? Okay, so here we've got our table, right? 7 hypnotized had the correct identification, 17 control did. 33 hypnotized had an incorrect, and 23 control had an incorrect. So we'll make this a 2 by 2 table, right? So our row total across the top is 24, across the bottom is 56, and our columns are 40 and 40. Okay, what we should expect out of that first row, right, 24, we should expect 12 and 12, and out of the bottom row, 28 and 28. Okay, so we're going to do these calculations, and we're finally going to get a chi-square of 5.94. Our degrees of freedom is 1. So our chi-square is 5.94, and in the table it's 3.84. So we can reject the null hypothesis that hypnosis does affect. And conclude that hypnosis does affect how well we recall eyewitnesses. Okay, what do we do when we have several groups? So here we've got a 3 by 3 by 3, white, black, Latino. Okay, we're going to do the same thing except now we have 9, right? So here's our calculations. Here's our table again, and we get a chi-square of 7.373. Okay, the table is 9.49, so we cannot reject this chi-square. We cannot reject this null hypothesis. Okay, we also want to correct for small expected frequencies because chi-square cannot just be used indiscriminately. Very small sample can be a problem. So if you look at this down here, right, we've got, when we look here at these different types of weapons, right? Look at these 2 that I have circled, right? Only 3 females used a blunt object and 6 used other. Those are really small things. So we might want to collapse blunt object and other together. We want to have gun, knife, and other. Okay, we can also use Yates correction. We collapse them, we're going to use Yates correction. So things to think about for two-way chi-square. 2 or more samples to be compared. Nominal level data, which we haven't talked about in a while, random sample, and they shouldn't be too small. All right, so that's the most important one, but let's talk about a couple other. The median test. We can use this with ordinal data, right? So what is the likelihood that 2 or more random samples have been taken from populations with the same median? Okay, so remember where the median is. It's that middle point, okay? And we want to create a crosstab with the 2 categories and scores that fall above the median and below it. Then we're going to use a chi-square test. So suppose a police chief wants to study urban versus rural police officer reactions to confrontational situations. He wants to know, is there a difference in the readiness of officers to call for backup in dangerous situations? So the research division of a police department shows a sample of 15 urban and 12 rural state police officers, a videotape of an interaction between a police officer and a citizen who's been pulled over for suspicion of DUI. The officer approaches the car. An apparently inebriated man gets out, walks towards the officer, and starts yelling. At this point, the tape stops, and the officers are asked to predict what they would do if they were that officer. And they're asked to rate on a 20-point scale the likelihood they would call for backup. Okay, and so here's all our guys' scores. So we want to find the median of the 2 samples combined, right? So it's the 14th position. So we need to line up all our scores and find the one that's in the 14th position. Oops, wrong way. Okay, we want to count the number in each sample that falls above the median and not above the median, okay? So in urban, there's 10 scores above the median, and in rural, 3. And in urban, 5 scores below, and in rural, 9 scores below. Okay? Now we're going to do a chi-square test of significance. Right? And here's our tab. So our chi-square is 3.13, but the critical value is 3.84. So we cannot conclude that there's a difference in readiness to call backup between urban and rural police officers. So we need a comparison between two or more medians, ordinal data, random samples. All right, now let's look at the Mann-Whitney U Test and the Kruskal-Wallis Test. So the median test ignores specific rank order of cases. This is looking at rank ordering in cases, whether the rank values for a variable are equally distributed throughout two samples. All right, so remember our n's are sample size, right? We have our sum here. Okay, so the smaller of the two U values is used for testing the difference between the groups. We're going to compare that against the critical U value table in Table G in Appendix C. Okay, so on a random basis, a researcher examines the arrest records of 9 female police officers and 9 male officers in the same department during their first year on the job. Number of arrests by gender is given in the following table. Note that the number of arrests represents interval data and therefore can be treated as a score, but because it's skewed, right, and it has small sample, we really don't want to use a t-test here. So we're going to put all the scores in order. Right, we're going to rank them, beginning with the smallest score. So all scores should be ranked from lowest to highest. A rank of 1 should be assigned to the smallest score and 2 to the next smallest score. Okay? In the case of tied ranks, take an average of the tied positions. So like there's 2 officers tied with 18 arrests, so we're going to assign them both a rank of 13.5. The average ranks 13 and 14. Okay, sum the ranks in each group. Substitute into the formula. Okay, and here we're going to get, we got our formula here, okay? So the obtained U in this case is 25, and it has to be smaller than the table value, in this case 18. So we're going to retain our null hypothesis. So we're going to calculate a z-score here, and the obtained z-score has to exceed the table critical value of plus or minus 1.96. So we do conclude that the difference in ranks between the two groups is significant. So again, comparison to 2 independent samples, ordinal data, random sample. Kruskal-Wallis can be used to compare several independent samples, ordinal level data, okay? And here's our formula, and we're going to use table F. Okay, so nursery school children are randomly assigned to see one of 3 film sequences. And the first one child attacks another and then is shown enjoying himself. In the second, the child engages in the same behavior, but the second child retaliates and overcomes them. And in the third film, the 2 children engage in vigorous but not aggressive play. Okay, so then they observe the kids and they see how many aggressive acts they engage in after watching this. Okay, so here's our scores for each of our 3 models. We're going to rank order them. Going to sum them and substitute them into the formula for H. Okay, we're going to get our degrees of freedom, which is 2, and then a 2 degree of freedom at alpha 0.5. Our critical value of chi-square is 5.991. Our H is 11.04, so we can reject our null hypothesis. Comparison of 3 or more samples, ordinal data, random sampling. Okay, and that wraps up our non-parametric measures.